James Kahaya, Research Director at TwoSix Labs. TwoSix Labs is a premier R&D company and technology products company working out of Arlington, Virginia. Our primary focuses are cybersecurity, data science, electronics, and cloud-hosted platforms for national security. So you can think anything from situational awareness type platforms to sensing platforms where we aggregate large amounts of data from scaled fielded sensors throughout regional or cityscapes, and analyze and aggregate all that data in real time and promote it to end users in an intuitive way. In addressing SOCOM's CWMD problem statement, the teams present were encouraged to collaborate amongst multiple companies to come up with a solution to solve the requirements needed and provided under the Golem end-to-end system. SOCOM used the AIM effort to fund a rapid prototype of an end-to-end system that showed proof of concept for dual threat detection from a platform called the GBall. This sensing platform houses both radiological and chemical sensors and transmits their data over Wi-Fi or LoRa over potentially long distances and long durations using a low power compute and communications protocol. That data is then sent to the Sigma backbone, where it's curated and analyzed in real time by a cloud-hosted platform, and it's additionally relayed by Sigma to the TAK interface for promotion to users interested in details that are more specific to the operational situational awareness type use case. To do that, they helped us assemble a team made up of TwoSix Labs, responsible for basically communications aspects, handling data, the cloud-hosted infrastructure, and user interface from the web-based standpoint, as well as relaying data to TAK. Nuvia Technologies and EasyMap, who were responsible for the GBall platform, and Design West Technologies, who's responsible for the very novel CNT-based chemical sensor. The project was commissioned to rapidly prototype and prove the concept that there could be a configurable, multimodal, multi-threat sensing sensor platform that could communicate its data over long duration and long distances, and was deployable via UAS, via drops, via UGVs, or being tossed or thrown by an operator on foot patrol. And that data could then be actually used by operators either in the field or back at C2. So there was an aspect of needing to be able to transmit this data over long distance, aggregate and analyze, and then present in an intuitive and meaningful way on the platforms that the end user requires.
I'm Chad Blair with Design West Technologies, a small business located in Southern California. Design West Technologies is an engineering and precision manufacturing company. There's two primary portfolios we focus on within the company. That is weapon systems and CBRN. Inside of weapon systems, we get into the electromechanical, the inner workings of systems, be that towed artillery, mobile platforms, and shipboard. On the CBRN side of the house, we focus on two areas. That is on the protection side and on the detection side. Design West Technology has more than 20 years of experience executing contracts for U.S. government agencies to include Department of Defense. We work on weapon systems and CBRN platforms. Inside of CBRN, we focus on protection and detection. Our chemical sensor work primarily focuses on carbon nanotube-based sensors. What's unique about the project that we teamed up with TwoSix as part of the AIM 1.0 is that we brought our sensors to life in a deployable means, plugging our sensors into communication means and other sensors They can be deployed on either the battlefield or other environments where it's important to have a safe distance, be that the warfighter or other operators or the general public, to give them a safe distance of either a known threat or a sensed threat. Getting our chemicals, our chemical sensors paired up with the GBall, deploy it for that standoff detection.
My name is Maria Bauer. I'm a program manager at Design West Technologies. I work in the R&D department, and that's how we entered the project. And what Design West Technologies brings to the GBall is what we call a matchbox. What the matchbox is a chemical sensor, chemical detector. The way the detection works is that it is based on a chemi-resistive electrode array. That means that's a multitude of electrodes that are coated with carbon nanotubes. And then on top of those carbon nanotubes, we put selective formulations. So that's a variety of different chemicals, and they react differently to the same molecule that they are exposed to. So let's say ammonia attaches to the chemical sensor. The different electrodes will give a different signal, and that creates a pattern. This specific pattern is unique to that one chemical, and that is how we identify it. So we have a processor inside the matchbox. If you want, you can call the chemical detector, the electrode array, the nose, and then the processor is the brain, and then it just outputs what the actual pattern recognition says. Now, it is a point detector. That means the sensor has to be exposed to the gas. That's also the reason that we integrated a blower inside the matchbox. It actually actively pulls in the gases from outside the GBall. So it has to be in a contaminated area, but it will then report out what the identity of the gas is together with the alarm. Nice thing about working together with TwoSix on this project is that this data that is outputted from the sensor goes all the way to Sigma and is displayed in Sigma. And it really allows you to go back on a timeline, see all the different alarms that have been triggered before. So as part of this project, we've been triggering a lot of alarms from our location in Tustin, California. And they are all in Sigma, they all still show up there. So that's kind of a neat thing. So you actually see a history of different alarms.
The nice thing about having a configurable data transmission capability is that an operator can be streaming data at anywhere from 10 to 30 seconds to a minute at a time, getting frequent updates on the radiological environment, the presence of a chemical threat. But if an operator needs to leave something unattended to function autonomously and provide long-term, long-duration sensing to cover an area, then you can extend that data transmission rate out and have that autonomous system remain in place to cover down on, with up to thousands of GBalls in a single deployment, potentially large terrain areas. So one of the chief general goals of the project was to give any entity from individual operator, unit, to battle space owner, a tool that they could use to easily discern whether or not a specific spot or a large area is safe for their personnel. The GBall accomplishes that through its configurability and the ability to sense multiple types of threats in the CBRN space. On one hand, we have the what we're calling the CS version of the Golem GBall, which is the chemical and spectral sensing, radiological spectral sensing GBall. And then on the other hand, we have the ChemDose or CD dosimeter plus chemical sensing version. The spectral sensor offered in the GBall is based on a well understood high resolution CZT technology. And the really nice thing about this is it gives us the ability with this very lean platform to deploy in a very agile way in an extreme or austere environment and actually get some kind of classification and identification back to the end user on the ground, but also to somebody sitting back at C2 who wants to look at the technical data via Sigma. So there really is a neat opportunity to provide both a broad sort of health and safety measurement through the dosimeter, but also this nice ability to actually adjudicate what it is that you're looking at in the field by virtue of the spectral sensor that Nuvia and EasyMat include in the GBall platform. Showing that was accomplished today, we were able to not only field the GBall successfully, but also create the alerts on the chemical side and on the radiological side to make sure we can cover down on this dual threat sensing type capability. I think the ability to have a small, easily deployable package that can sense multiple things is really kind of at the core of what that safety requirement was. And then I think the rest of that requirement was sort of covered in the future extensibility of the platform to incorporate other sensors, whether those be additional chemical sensors or biological sensors, and the scalability of the platform. That scalability, of course, is accomplished through the real linkage of not just the communication standards and capabilities inherent to the actual GBall platform itself, developed by Nuvia, ATAK, and EasyMap, but also the ability to actually offload and ingest all that data in real time through the Sigma architecture, and then get that out to operational users in an actual meaningful and usable way that doesn't overburden the TAK ecosystem in the field. TAK is a place where everyone through law enforcement, through DoD, have found huge value in the more real-time operational battlefield type situational awareness overall. And so what we really wanted to show was how this more technically oriented platform could be complemented by the operationally situational awareness platform in TAK. Sigma accomplishes this by relaying specific information to TAK in a more lean way. So TAK doesn't necessarily need all the streaming data, but you can configure our relay service to send sensor location and alerts so that operators have an understanding of health and safety impacts to them and in the vicinity of sensors in the field in near real time.
These are the guts of the GBall, so to say, so that's what's inside the GBall. It has on one side the part that TwoSix put together, so that's battery, communication, charging, and so on, as well as the RIN detector. And then on this top hemisphere of it, that's our chemical sensor. So this is the matchbox that I'm talking about. You can actually see the fan that is actively spinning in there right now. And then this separating wall ensures it seals towards the upper hemisphere of the GBall, and it ensures that air is not just recirculated within the GBall, but that it actually actively drags it in on one side and blows it out again on the other side. So we've been dropping these for our tests, for example. We've been dropping these on like a painter's cloth that was soaked with ammonia. You do not necessarily have to throw the GBall directly on top of the ammonia, but if you throw it anywhere close to it, it will pick it up. It really always depends on the concentration of the analyte that you're spraying out there. If it's a very high concentrated source, then you will still sense it far away. There's also, of course, some wind modeling and things like that that you could get pretty deep into to analyze where you place the sensors. The nice thing about the GBalls, though, is that you're actually talking about not just one GBall, but they have a bunch of those GBalls, and you can just throw a few out there in a suspicious area. So it's not necessarily just that one location where you're sampling, but you can be sampling at multiple locations.
Today what we tried to capture on the deployment side was how easy it is to deploy a GBall and how rugged the form factor is. The reason that is important and unique to CBRN is much of the technologies included in the GBall that do the sensing and do the electronic communication and compute portions are otherwise relatively sensitive. So what the team was able to accomplish is take this otherwise sensitive technology, package in a way that it's ruggedized and deployable, and show today that it could be dropped by UAS or thrown out of a moving vehicle. This is pretty critical for end users, not just because the deployed environment is a difficult and sometimes dangerous and rough one, but also because these sensors need to be able to be deployed in a more agile way, giving operators greater standoff from potential sources of harm.
My name is Chris DeBobin. I'm with representing Robodub and Marengo. We've got a morphing drone concept that's been able to redefine how we think of safety and resilience in the face of hardship at the edge. And so the idea behind the morphing technology is to be able to provide a safety outlet that's not a parachute or an auto rotation response to an engine going out or an arm failure, and most importantly, to allow for asymmetric loads. So a lot of different drones, when you think about quads, they're fixed on 4 different points. And when you put on asymmetric loads, things that are long, things that are heavy, you need to be able to have a response that optimizes the payload. And so what we found is between 12 and 18% increase efficiency over distance by having the arms shift to optimize where the motors are responding to that center of gravity. So it's just a shifting response of where that center of gravity is. And then because it's a living response, when you drop one, it then shifts the center of gravity to respond to the new center of gravity. And the overall design and concept right now is in the prototype phase. It's proven itself, at least reliable enough to transition and get into the field. It runs a really light footprint when you think about logistics and point-to-point distribution. With 4 of these drones carrying 10 kilograms net capacity, 4 drones can support an entire infantry rifle company's class 1, 3, and 5 per day. We were able to work with TwoSix Labs and Design West, taking their sensors as a proof of concept and deploying them out. Right now, we've remained isolated to lines of sight, but right now, with enough integration of the right communications equipment, we can go beyond visible line of sight. And then at that point now, the West and TwoSix platform can be a node of knowledge, and then also it can instigate or be a catalyst to additional responses from our system. So if you have 2, 3, 4 drones all loaded down with additional sensors, that when a sensor is triggered, you can validate whether or not that sensor that went off was a false detection or a real detection. And if it was a real detection, now you have the ability to paint the cloud as it moves. So the first 2 drones are painting downwind of that observed sensor reading, and then where that cloud moves, whichever elevation it's moving, downhill, you can keep ahead of it. And so you're only putting at risk a drone that, if it is contaminated, can either be disposed of or sanitized and cleaned. And I think that's a critical element to this as far as force multiplication with one person managing this entire fleet, or force preservation with not having individual humans in the potential danger area.
One of the big benefits of the GBall platform is that it's extremely modular and configurable. Configurability extends really to the rate at which communication occurs, and that extends your potential for long duration on the power side, theoretically almost as long as you wanted to. So I think we're looking at anything from days to weeks to potentially months on the very longer end of it. We used Wi-Fi and LoRa today when fielding the GBalls. The GBall platform, built by Nuvia Technologies and EasyMap, can communicate between up to 250 GBalls at one time in a single gateway. The gateway needs to be paired with some kind of compute and backhaul platform. Today we used cellular infrastructure just to get the data out of the field. And so, we showed today that concepts work. You could scale out to much more sensors than we did today, of course. And the next thing we also showed was that LoRa can be leveraged to extend range. Today we only got out to about 1,000 meters on a medium power setting, which is pretty good for such a low power platform. So we were pretty happy with that. Additionally, LoRa can also function in sort of a pseudo mesh way, relaying data between GBalls. So there is an opportunity to really extend range with an array of GBalls, allowing them to sort of daisy chain data out beyond whatever the initial GBall field it is. Part of the core of this project was accomplishing this dual threat sensing platform and capability. And NVIDIA Technologies was absolutely integral in combination with EasyMap in providing this and augmenting or evolving their existing GBall platform to accommodate an additional sensor. Now, one of the big objectives of this whole thing was to do this in a way that the both physical and communications protocol used to extend the existing GBall platform to other sensor modalities was that it was designed to be extremely open, making the overall system very modular and configurable. And they accomplished this, I think, in spades. What they've provided with the GBall is not just the proof of concept for a dual threat sensing technology, but one where one hemisphere, dedicated in this case to chemical sensing, could also be used for an additional sensor. It could be a different type of chemical sensor that you could plug in here. You could bring in some kind of novel small biological sensor. And the nice part about that is that those developing sensing technologies don't really have to worry about how am I going to get data out of the field, right? They can just if they can get into our form factor and they can accommodate our comms protocol, then they have a solution for getting their data out of an expeditionary environment and backhauled to a system where it can be curated and analyzed in Sigma and saved and made available to users both in near real time, but then also for all time if desired. So there really is a neat opportunity to provide both a broad sort of health and safety measurement through the dosimeter, but also this nice ability to actually adjudicate what it is that you're looking at in the field by virtue of the spectral sensor that NVIDIA and EasyMap include in the GBall platform.